is a picture from Dr. Ackman's paper showing the polyglucosan body disease mouse, and you know the colors are a bit different from what I had shown you, but it's just because it's a different lab, a bit of different colors. But you see all the polyglucosan body accumulations here in the liver, here in the heart. In the muscle, if you look at this faint pink here, you see how every single muscle fiber has polyglucosan bodies, and also in the brain. It's a bit hidden on my screen because of the webinar thing, so I can't point out, but you can see the polyglucosan bodies. So that's the first experiment that we are proposing to do. I'll just go back, and namely it's this experiment, breeding the Orhan's mouse with our PTG mouse and studying the mice the same way we studied the Lafora mice, and prove the principle that by reducing glycogen synthase, we can stop adult polyglucosan body disease. At this point, I would move to the second experiment, but perhaps it's a good time to take a pause and see if anyone has questions about the first experiment.
I'm looking for raised hands, but in the meantime, could you just make a distinction between the two mice that Dr. Ackman is going to be sending you, the wild type as well? And I'm going to unmute Dr. Ackman just for a moment here anyhow, in case he wants to chime in. You're live, Dr. Ackman, so don't say anything we'll regret.
So let me start, and then Orhan can fill in. It's a little bit complicated to explain, and maybe you can explain more. To get the branching enzyme deficiency, he had to manipulate the gene in certain ways, and they were able to get a mouse that is forming polyglucosan bodies everywhere, including in the brain, in an age that is appropriate for experimental research. So within the first 6 months of the mouse's life, the mouse has polyglucosan bodies, so we can study it. It's neither dying early, nor do we need to wait 2 years before it makes polyglucosan. So it's a great model to use, because within 6 months, we can know if we were able to get rid of the polyglucosan bodies. To explain the genetic manipulations that he did, I mean, if you want, I can try, and he can definitely do it better than me, but that'll take some time and it's technical. Orhan, did you want to add anything?
Orhan?
No? Yes. Yeah, I am here. No, I don't need to add anything. Only I would like to say, as Dr. Minassian explained, we decreased the expression of GD1 in the mouse, and it affected all the tissues. And as he said, the advantage is the mouse develops the polyglucosan body early in life, so we don't have to wait really long time, and we can breed two mice together and see the effect quickly. Right.
Are there any other questions about this section?
You mentioned that you're seeing polyglucosan bodies as a matter of course, in other people, it's a natural thing. Is that a sign of aging? Is that, do we see more of that as we age?
No, there are polyglucosan accumulations in the brain related to aging, but they are not in neurons. They are in what we call glia or astrocytes, and that's normal. The problem in both these diseases is that the polyglucosan bodies are accumulating in neurons. Normally, you do not see polyglucosan bodies in neurons in anybody other than in these two diseases.
Thank you.
Any other questions?
Dr. Ackman, are you there?
Yes. Yes, I'm here. I can hear you.
A recent patient, though, that just had the brain, polyglucosan bodies in the brain, right?
Yes.
So there are other diseases that are out there that do show polyglucosan bodies?
There are other diseases, at least for PFK, which is actually mostly in the muscles. But the particular disease that we have talked before, there's, I cannot really say it is GBE1 deficiency because
Yes.
enzyme activity on that particular patient only 50%. And obviously there are other genes which is involved in the disease. And we have to search for it and find out. But we couldn't find any mutation in the other genes that works in the glycolytic pathway or glycogen synthesis pathway. So this is still unknown, and we are searching for it.
So you would theorize that there are other diseases that have polyglucosan bodies in neurons that just haven't been discovered yet, or that we don't know?
Yes, there are other diseases that we don't know the molecular background, so or mutations that cause the polyglucosan accumulation, or at least that particular patient that we have. We talked before. Unfortunately, I am here in Houston today, and I don't have anything that I can show about that. And the patient that we are talking had a severe polyglucosan accumulation, and it is only in the brain. And there is no muscle involvement or any other tissue. And patient didn't have any myopathy or neuropathy, but disease developed as dementia and they deteriorated very severely in 4 years. So we know that the patient is heterozygous for one GBE1 mutation, but it doesn't explain the severe disease. And we are looking for the other mutation if there is. Right. So, I mean, obviously there are other modifiers or the reasons for the polyglucosan accumulation, and they are to be found.
Dr. Coughlin, I'm going to just unmute you. I saw your hand go up, but...
Oh, thank you. Just a little comment. First of all, polyglucosans are also found in the brain in Alzheimer. This has been observed. But again, as Dr. Minassian said, it's in astrophia, not so much in the brain, but there is accumulation found in the brain. And the second comment is that I have preliminary results, which I hope to be published soon, that shows that also in a neuronal model, in which the accumulation of polyglucosans is inducible, reduction of glycogen synthase can alleviate the burden of the polyglucosans. So it can remove polyglucosans also in a model. That's what I wanted to say.
Thank you. First?
Yep, I'm here.
Okay. Where's that? You want to continue?
Sure.
Any comments? There we go.
Okay, so that was part one of our proposal that some of you, I guess, have. And now I'll go to part two. So, everything I discussed before, by the way, what you're seeing here on the screen, if you look here on the left and the bottom, this is an axon of a neuron. You see the myelin sheath around it, and inside it you see the big polyglucosan body that's clogging it. And here's a cartoon of this real picture. What I described now is a method to stop polyglucosan formation. So you can imagine a new onset patient coming to the clinic at age 50, with signs and symptoms of the disease. At that point, they are not very sick. They have just the initial symptoms. And if they're diagnosed quickly and we can treat them quickly, then the disease theoretically should stop and not progress. So this would be a huge advantage if we had a medication that stops the disease. But I think, and this is hopeful speculation, it is not fact, in my estimation, these polyglucoside accumulations are a net accumulation between uh, making between a lot of formation and some elimination. I theorize, I suspect, that the cell is constantly trying to get rid of them, but more are being added than the cell is able to rid itself of. So there's a net accumulation that over time, clogs the axons. If this theory, if this speculation is true, then if we stop the disease in the fashion I described before, then the cell may be able to clear what's there as long as there is no net accumulation, and therefore our treatment may result not only in arrest of the disease, but in a cure, meaning the polyglucosans may be cleared. That we will only know when we find a way to stop the disease. If this is incorrect, meaning that if what we achieve with the previous experiment is simply to stop the disease and not to eliminate the polyglucosans that were there before we intervened, then let us say a patient who has already advanced disease and they have a lot of symptoms, we may stop the disease in its tracks, but we may not be able to reverse the problem and remove what's already been accumulated. So this next experiment is an attempt towards a direction to try to remove what's already been built up in a patient. If this works, it would target patients who already have advanced disease to get rid of the polyglucosans and return them to a normal state if possible. Now, the only thing known to man that can digest starch is amylase. Amylase is an enzyme that we produce in our salivas, in our intestines, and which we use to digest the starch that we eat from plants. So we humans are able to and make amylase normally. The thing is that we only make it in our digestive system because that's the only place we encounter starch normally. So we have the ability to make the amylase, but we don't make it in brain cells, in neurons. So the idea is, and this has been a long-standing idea of ours, that if we can make if we can have neurons make amylase, or if we can get amylase into the brain, it would go and target the starch and digest it. Now the advantage of this approach would be, if we can do it, this is a harder experiment than the previous one. It involves getting a protein, an amylase, into the brain. But the thing is, if we can get it in only one time, then it will digest what's been accumulated for 50 years or 60 years, and that's it. We don't need to get it in again. The patient can then form new polyglucosans for the next 50 years of their life till they're 110 years old, and we won't need to intervene till then. So this would be a great thing if we can get amylase into the brain, into neurons, one shot. Not easy, but a possibility.